Thank you.
Thank you so much, you guys. I appreciate it, Naira. I'm under the impression I just confirmed that you guys can see my presentation. It's sampling-based full diagnosis, my PowerPoint, right?
Yes.
Okay, so the title of my presentation today is sampling-based full diagnosis and change detection for stochastic dynamical systems. My name is Ioannis Raptis. I am an assistant professor at North Carolina A&T State University in the Department of Electrical and Computer Engineering, and I'm going to present you my joint work with my graduate student, Vincent Wow, from whom I obtained many of the slides that you're going to see today. So, getting started, a little bit of how the presentation is organized. I'm going to provide you with some motivational remarks and then discuss how nonlinear state estimation can be used in our novel framework to conduct full diagnosis. So this is going to be the core contribution of this talk, the main theme. Then we're going to transition. The second part is going to involve transitioning to show how this the proposed methodology can be used in practice in order to identify faults for our rotorcraft. Results are going to continue and some concluding remarks. So I'm going to start with some very fundamental terminology, which obviously is known. It's already known. Now, there is a complaint for Dr. Ramsey, I believe, that there is no audio. I really hope that this was resolved. Sorry for this interruption. James, I don't think I can do something, unfortunately. So, what is a fault? Well, a fault is a deviation from expected operations. And I'm going to be more specific later on and defining a fault as being a change to the dynamics of a system. Now, aircraft in particular is susceptible to faults that may lead also to catastrophic failures. I mean, this is obvious. There is a safety critical application, and they can be the typical faults that aircrafts are subjected to can be categorized to sensor, actuator, or structural faults. We're gonna focus today on actuator and structural faults. Nevertheless, we have developed a framework which works equally well with faults for sensors. Now, regardless of what fault you have, the timely diagnosis can improve what we're looking for, which is averting downtimes, breakdowns, and catastrophic failures. Now, pretty much the idea is for fault diagnosis is to have algorithms to replace as much as possible the redundancy of hardware, which is cost ineffective. And the idea is to promote algorithmic software-driven solutions. Now, our approach is classified as model-based. Why? Because we are using a mathematical description of the system at hand to determine the severity of the fault and define the fault itself. Model-based fault diagnosis techniques, it is an established methods with well-known results. Now, moving forward, we also introduce a sampling-based method, which is particularly suited for high-dimensional systems, and for ones that they are subjected to high fault spaces. There are many fault modes, and aircraft and in general aviation is an application domain which is characterized by this necessity. So what I'm going to show you is how computation can be used in order to solve efficiently and to the best extent possible problem that would be else very analytically laborious to solve. So what are we going to do? We're going to develop a sampling-based, sampling and model-based method for fault diagnosis that can handle analytically intractable, non-linear, non-Gaussian aircraft dynamics with algorithmic implementation. So in other words, it has a straightforward transition to an integration to an embedded system. So at the end of the day, we want also, one of the requirements of our design is to produce something that can be easily applied by someone to their own system and to their embedded system that typically monitors, typically supervises their application. So Vincent was patient enough to put this very nice landscape of fault diagnosis techniques. As you can see, the main category is knowledge-based methods. This is what used to be referred to as the quote-unquote intelligent methods in the past. We're also having model-based, the most traditional approach, which is model-based methods. You may recognize the parity space, what was used to be something a popular technique, and the classical notions of parameter and state estimations. As you have realized, the last years, data-driven methods are here to stay, and pretty much data are substituting traditional physics-based and first principles models. So I'll just give you, I mean, obviously, you can perceive what I'm going to show you today is something more traditional. It is, we're still going to see a nonlinear difference equation today, and we are sticking to our guns that models are still useful and perhaps necessary. Now, and we can discuss about it. Now, a little bit of a historical perspective. I'm going to go through certain milestones. Whoever is interested in educating themselves in this domain, they should be aware of. So back in the early 70s, we're having what is the Nuremberg observers. These are observers directly suited for, they started for linear deterministic systems. This is a classical observer design that we, like control engineers, are aware of. Now, Kalman, the use of Kalman filter for fault diagnosis first appeared by Mehra and Pesson also in the early 70s. This is a paper that is difficult to find. Now, we had the first tests, the first decision-making processes for fault diagnosis, and I'm going to emphasize the work of Whiskey back in the mid-70s. And I mean, essentially, then, like, Whiskey's work dominated the entire 70s. And the major the major development, this is back, like I would say in the 90s, suboptimal filtering, like in other words, particle filtering was becoming popular. So another milestone, I would say, it was the early 2000s that there was a series of works of Kadi Kramanathan that defined suboptimal estimation, in other words, or what is well known as the particle filter, to be used for the purpose of fault detection and identification. So how does a conventional model-based design looks like? Well, you're having a real system from which you obtain an abstraction. This abstraction is its model, and it's manifested in general by some sort of law that governs the state of the system with time, like in other words, a differential or a difference equation. The system itself can be deterministic, Gaussian, so it can be also stochastic or random, with perturbed by Gaussian or non-Gaussian noise and combinations of these two elements. So for the system, we develop an algorithm. We develop an estimation or observer method, like observers for deterministic, we traditionally call estimation or filter for stochastic systems. I mean, typical examples is Kalman, the Leuenberg observers again, the extended Kalman filter, uncertain Kalman filter, and the particle filter. Essentially, the Kalman filter, the uncentered Kalman filter, and the particle filter are the three schools, the three primary directions of the estimation problem. Integral part of the process, it is the collection of measurements from sensors, which are compared to the information that we obtain for our understanding of a model, and this is used from a decision logic. So this is another part of fault detection and identification. It is the decision theory, for which we make a decision whether or not a fault is present, and if we consider a fault being present, what is the cost of our choice if we are wrong, for example. So traditionally, I mean, when it comes to model-based techniques, the most common architecture when we are dealing with multiple fault modes is to have what we call the bank of estimators. Okay, so pretty much, essentially, you're making an estimation, and if there is, for example, lowercase n fault modes, for each of these guys, you're running an estimation. You're estimating the state of your system at every time step for all of these fault modes. And for all of these estimates, you do some sort of a test whether it's more likely to have a fault compared to the healthy or no fault operation. And then based on this test, you're making a decision. So this is where we're coming. This is where we're coming into play. And well, we want to substitute one of the things that we want, one of the contributions that we want to accomplish is substitute this process of bank of estimators, which with another mechanism, which hopefully is not hopefully, we have established that it is more computationally tractable. I mean, we're saving in terms of computation, and at the same time, it elegantly provides. It also provides reliable FDI, fault detection and identification results. So what we are using as our estimator today. You're gonna see a variant of a particle filter. So even though we're talking about detection and identification, we're gonna have the main core of our work is an estimation. It is an estimation technique. So essentially, we are doing this modification in order to be safe in terms of computation, and at the same time having an informed manner, and a manner that makes sense when it comes to figuring out if a fault mode is present, or in another impossible feature, if multiple fault modes are simultaneously present, which in general multi-model hypothesis testing is limited only to one active hypothesis being present. So let me start by providing you a mathematical description of the problem at hand. I'm starting with a standard non-linear difference equation, and consisting of what you see with green is the nominal dynamics or the healthy dynamics, and there is this step function veta, which is activated at an unknown discrete time instant k0, and introduces to my system whatever you see in red, which is supposed to be a change in its dynamics. Obviously, what you see with blue, marked with blue, is supposed to be colored with blue, is also the model uncertainty noise, for which my approach is not going to make any, it's not going to limit. But typically, this is Gaussian noise. So I need to emphasize that compared to other methods, and of course there is not one global approach. This is not a method about identifying the presence of exogenous signal or some type of determining residual. This is about figuring out changes in the dynamics of your system. And perhaps one shortcoming of our approach, like one of the weaknesses that I can also share with you, it is that we are expecting the fault dynamics to be known so far. I mean, we're still working off bypassing somehow this limitation. So again, I mean, you need to have a node model in our technique, and also we're trying to argue that okay, if you do not have an exact model, then okay, you better do well in the presence of model uncertainty. So again, these Vita functions, for which I know nothing about, introduced at unknown time instances, and for whatever reasons, they introduce changes to the dynamics of our system. Now, the description of Vita can be some sort of crisp change to the dynamics, where these Vita functions are step functions, essentially, or they can be incipient fault modes. I mean, they are gradually creeping in to the system and can be represented by, for example, a first order step response. Now, after this point, the number of fault modes is uppercase M. Now, keep in mind that based on this modeling approach of my process model, which is defined by S, we can have multiple faults occurring. In other words, you can have loss in one and then to a second engine of your aircraft. So what is the outcome? What is the output of what we are producing? It is a statistical characterization of the fault modes that can trigger some sort of a fault alarm. In other words, there's a decision-making process based on observations from my sensors. Okay, I'm coming back to dissect a little bit. I'm coming back to dissect a little bit the difference equation and the process model that I just described to you. And in particular, I'm going to talk a little bit more about these step functions, this collection of M, uppercase M, step functions that are supposed to introduce the faults to my archetypal system. Now, they are so important that I'm gonna do, what I'm gonna do is that I'm gonna get this bolded vector uppercase B, and I'm going to insert them into an array. So this essentially, this super vector represents any change that's going to take place from the system. Every transition of these elements from 0 to 1 represents the occurrence of a fault mode. So this is going to give me a more compact description of my difference equation, where all of the presence of the change in the dynamics are represented by this upper G function. Now, a little bit of some key features that make the particular problem different from what is known in signal processing as signal processing and control theory, I would say, of the model selection. In other words, figure out which model is active. We're going to talk more about it. Well, you know, one of the things is that faults are supposed to be persistent. If something breaks, it does not heal itself. So when theta becomes 1, it's going to stay for every time, and for every time one of these theta functions become 1, it's gonna stay 1 for every time instance after the time instant that the fault appeared. Now, the model that the reason the state transition, like the transition from going from this theta function going from 0 at a time instant k minus 1 to 1 at time instant k, in other words, the mechanism of which the fault occurs is unknown to us. We do not have any a priori knowledge of the probabilities that something may break at any time instant. And also some other variant that makes our problem somewhat unique is that the multiple fault modes. So the identification challenge is even bigger. There are multiple fault modes that may occur at various time instances. Okay, let me give you a little bit of a discrete event viewpoint, because sometimes fault diagnosis in this context is done from the focal point of discrete event systems. So assume that based on the description that I just gave you, assume that we're having uppercase M fault modes. Well, considering the fact that we can have multiple faults occurring from a discrete event viewpoint, and the math are very easy, you may have 2 to the m possible states. And keep in mind that so it is essentially you're taking the k combinations for all k where the number of elements is uppercase m. Now the combination of m with 0, this is corresponds to the healthy state. And if you try and just to give you an idea, to give you an illustrative example, if you consider 3 fault modes, you're going to end up with 8 states. So as you can see, the number of states increases dramatically with the number of geometrically with the number of fault modes. So let's see here the discrete event transition going from the non-fault we always consider ourselves starting from the no-fault state, and then one of them may occur, then a second may appear, and then a third may happen. Now, let me give you another viewpoint. Now, this was a discrete event viewpoint. Now, I'm going to show you another viewpoint, and all of these different viewpoints. The reason that I'm sacrificing time to show them to you is that because they forged the development of our own methodology. So consider the case. This is another classical problem, again in mostly in control systems and again in signal processing. Consider that we're trying to figure out which of the lowercase m models of lowercase m plus 1 models occurs based on noise infested measurements. The h equals 0, the index h equals 0 for your actually it shouldn't be h, it should be j. I do apologize here for the typo. The case for j equals 0 corresponds to what we refer to as the healthy model, while the rest of the lowercase m indexes represents the dynamics, the model that corresponds to a fault mode. So, I mean, pretty much what we need to figure out is obtain an estimate of, at every time step, we need to obtain an estimate of the state, and then conduct some sort of a test for, and we need to do that, for all of the possible models, and we need to perform some sort of a test like that we can detect a shift or a jump to the dynamics. So if you come back to our monolithic problem where we're having for m-fault modes, we end up with 2 to the m states. Our lowercase m, in other words, the number of our states is 2 to the uppercase. So as you can see, we are dealing, especially in problems which are characterized by high dimensional fault spaces. In other words, you're having many fault modes. We're dealing with the case of dimensionality, where the state space is increasing and the fault modes escalate the complexity. So in this case, the estimation problem, because essentially every time that you're going to need to run is an estimation, it's going to be computationally expensive, and it's going to be an additional computational cost to perhaps an estimator which is already characterized by increased computational needs. Like, for example, the particle filter is a well-known estimator that it is computationally expensive. Okay. So now there is a fourth perspective. This is the perspective of parameter estimation. Okay, I mean, you may consider any type of, in the case of the parameter estimation, it's the well-known problem. In fact, in the case of the dual parameter estimation and state estimation, you're having an unknown vector theta for which you would like to obtain an estimate of its value. Now, in the realm of parameter estimation and in general in the Bayesian, in the sequential Bayesian methods, a common approach is to model, like, to augment the parameter vector into the state dynamics. In other words, create a new state for your parameter vector, and its state transition model is represented by a Gaussian random walk. I mean, the obvious idea is to treat what we refer to as the change vector. If you guys remember this bold B vector as a parameter vector, but there are a few shortcomings in that approach. Well, we know from the literature that introducing random walks to your state transition model, it's going to inflate the covariance in the estimation part, and it's going to lead to more wide, more diffused posteriors. Okay, and also keep in mind that the parameter estimation problem involves parameters that are constant. In our case, the change detection, the change vector, is supposed to be something that changes. It transitions from one value to another, its elements. Okay, so as you can see, like trying to put everything, like if there's a takeaway out of the parameter estimation, is that the parameter estimation, like something interesting that we can take out of that thing, is that the dual challenge of parameter and state estimation is converted with the way that I showed you, which may not be very effective, but it is a way, to a single state estimation task. So you're killing two birds with one stone, essentially, in other words. This is done by treating the parameter, as I mentioned, as a state vector, and then defining a state transition. So this is definitely something that that it's useful to use. I mean, make your fault detection problem into an estimation problem. Like make something that provides both of these. Make a filter that supplies you with both of these tasks. So a little bit of a particle filters. I'm not gonna invest much time because I'm gonna show you how the standard particle filter is laid out, and I'm gonna do it through the lens of fault diagnosis. So you're gonna see how, like, if you are not familiar with the particle filter, how it works, like how the standard configuration is taking place. So I mean, pretty much the idea, and this is a classical structure for Bayesian, for sequential Bayesian estimation. You're having a prior probability, you're having the likelihood. This is coming from your data. This is a PDF coming from your data, and you would like to obtain a posterior. Now, the posterior probabilities are continuous, multidimensional, and typically they have, you are dealing with nonlinear systems, with nonlinear and non-Gaussian systems. So what do? We approximate them with discrete PDFs represented by a set of what we call particles and their respective weights, and and we are updating these discrete PDFs using special sampling techniques. Okay, there are special sampling techniques to handle the transition from prior to the posterior sequentially, and in a manner that's going to provide us reliable results. So just to give you an idea, a standard estimation algorithm in general consists of two basic steps. This is the prediction and the correction. These are the two steps. If you see a breakdown of my algorithm, the particle update corresponds to the classical prediction step. You predict, then you correct with the data. This is what we call the weights update portion. And there is an additional part which is really important, and this has to do with the computational aspects of particle filters. And keep in mind that particle filters are suboptimal solutions and approximations which were invented in order to solve analytically complex problems. So we needed to do something computational. We needed to do a computational intervention to make sure that these algorithms, their performance is not going to deteriorate. So what I'm going to show you is a dual method designed for fault diagnosis, which creates a state estimator, or what we refer to as a filter, which has a dual purpose: state estimation and fault detection and identification. So, for ease of reference, I'm gonna call this special estimator, the special filter, I'm gonna call it the failure sensitive filter. So we're gonna start first by describing how the state transition, how we should this filter. The manifestation of this filter is an algorithm that's supposed to process information coming from the actual process. Okay, so it is like at the end of the day, it's gonna be broken down into distinct steps. So what is the state of my FSF? Well, I'm gonna take the continuous. I'm gonna combine a continuous value, the state, which is which aspires to estimate my system dynamics, and also I'm gonna introduce a binary transition mechanism. Consider of uppercase M binary states, which are updated, which they have their own difference equation, and each of them is supposed to estimate the value of this of the change detection vector. So the collection of my binary states, I'm going to call it the calligraphical B, which is tasked to estimate what I used to call the change vector, which was the bolded B. And essentially, the statistical inference of the calligraphical B of the binary states is going to yield an estimate of the change vector. Now, because you're having, by definition, the binary states are binary, and at the same time, I'm having continuous valued states replicating the dynamics of my monolithic process. By definition, this is a hybrid filter. Now, because I'm going to use a very special way to evolve the binary states, is going to end up being a non-Gaussian filter. And the reason that I'm making emphasis of this being a non-Gaussian filter is due to the fact that the bootstrap particle filter, what I'm going to end up using at the end, is so versatile that it can handle non-Gaussian noise. So let me get started by the core of this. Let me get started by what is going to be this difference equation, this map essentially, that evolves my binary states. Okay, so remember that the binary states were introduced in the first place in order to do some sort of parameter estimation of the change detection vector. So it's a specialized way of doing that. And let's get started with first understanding of how the state transition model of the faults works. So I'm just gonna do a model, and I'm gonna try to make a model which I think it makes sense. And this, according to this model, if at a time instant k minus 1, your system was healthy, let's say there is a probability eta that you're gonna, high probability eta, that you're gonna remain healthy, and 1 minus eta that you're gonna transition to a faulty state. Obviously, the value of eta is unknown. I don't know what causes this thing, but there exists a probability that for which my step functions transition from 0 to 1, unknown. But I can model it this way, and it's kind of plausible approach. Now, if your state is 1, you're going to remain to 1 with a probability of 1. So it's certain that if your fault occurs, it's going to stay there. Your system cannot self-heal. So, I mean, let's assume that this is not a very restrictive assumption, that in general, eta is going to most likely have a high value. Things don't break that easily. This is not going to take any role at all in my design. So, I mean, somehow I need to also have a state transition PDF for my binary states that replicates the aforementioned distribution that I told you about the change detection vita. So I would like to make this random sampling map essentially, like this function phi, at the end of the day, performs a simulation. It simulates, it's like you treat the binary vector as the binary state, I'm sorry, as a random variable, and this function phi is designed to guarantee that your transition PDF for the binary states celebrates certain properties. Now, because this is going to be, because I'm going to be generating, I'm going to be simulating. In other words, I'm going to draw random numbers. In order to design my phi, I'm going to use uniform noise from 0 to 1, because that's the easiest thing to draw samples from, okay? And the idea is that the state transition PDF of the binary states is going to have at least the same structure with the same support. And support means that it is non-zero when my desired PDF is non-zero. They do not have to be the same. So what I do, well, I just draw a random number from 0 to 1. If my state, like if my state, my previous state is healthy, and then and the random number that I draw is less than a value eta tilde, well, in that case, well, you know, I set my new state equals to 0. Else, I'm going to set my new state equals to 1. And this is a very easy way to show that the updated state is a random variable, and it follows the same structure, it has the same model with what I just showed you here. The only difference is that because I do not know eta, it is substituted by eta tilde. And this is a designer's parameter, which I believe, I'm going to comment over here. Now, a value of eta tilde equal to 0.5, it means that the designer's belief is that there is likelihood to be equally faulty or healthy at the next time step. And essentially, phi, it is an ergonomic, the design of phi wants to provide an ergonomic means of inserting the binary state as random variables and seamlessly integrate them into the difference equation. So I just want to put a state, I want to introduce difference equation, right, which replicates the simulation of a state transition PDF according to my likings, and this is the case. So how to select tilde eta, I mean, you don't have to be accurate when it comes to this thing, but a fair assumption is to think that in general is not very likely for a fault to happen. And I'm going to show you in detail how things work. Well, how does my particle filtering operates? So I'm going to take the basic structure of the particle filtering. I'm going to use the model of the FSF that I just introduced and show you step by step how you can provide inference about the occurrence, or make a decision about the occurrence of a fault mode. In the beginning, you just draw uppercase N samples from, for example, a Gaussian PDF, and this is your pre-assumption about your initial state. It doesn't have to be accurate, but it helps. So, I mean, all of these, what we call them, those N particles, are going to be assigned with an equal weight. Remember, like at the end of the day, what we are doing is that we are updating a posterior PDF, which is represented by particles and weights. It's a discrete multi-dimensional PDF. So, okay, I'm just drawing N particles from my initial belief of where my state starts. I can use a Gaussian distribution which its mean and its variance gives me some sort of confidence of where my system starts. And I'm obviously assuming that I always all of the particles are healthy. In the following graphs that you're gonna see on the right hand of your screen, it shows a one-dimensional. In this example, in this illustration, I'm using a one-dimensional state. In other words, the continuous value dynamics have only a single dimension, and green markers represent healthy particles, while red markers represent faulty particles. And what do I do? I mean, when it comes to the sequential execution, we're having the state prediction step or the particle update. This is where you're using your knowledge of the model dynamics in order to progress the states of your the knowledge dynamics in order to progress the state of your system. I want to make the following comment that I design phi with the following qualitative guideline in my mind. I would like my phi at every time step to retain the exploratory nature of the binary state. In other words, I wanted, to transition with I just wanted for it to produce particles, a small number of particles that explore what we call the other side. Like, for example, I would like for it 90% of my particles to also entertain the idea that there might be a fault to the system. And again, how many of these guys are going to end up transitioning is a design parameter. Like, for example, for cases with high signal to noise, for low signal to noise ratios, exploring too much is kind of a bad thing because the PDFs overlap. So you're giving too much emphasis to things that you shouldn't have given. But again, these are cases that are difficult in general for estimation. What we're having is what follows is the state, what we call the correction part, or what is referred to in the particle filters as the weights. What you see as being the blue stem over here, it is your predicted value of the observation. This is what's this is what's coming from. Apologize. This is what's coming from the data. This is not supposed to be here. X, it's supposed to be the predicted, it's Z of X continues. Okay, so whatever you see with stems is supposed to be the predicted observation. Okay, now the blue marker, the blue stem here is supposed to be the observation coming from the data. Very simple. I mean, what the likelihood is gonna do in its most general form is going to assign with a weight, an importance to these particles for which are closer to what is coming from the data. Okay, so essentially in the weight update step, what we are doing is that we're putting an importance, we're putting some sort of an like literally a weight to each of the particles based on the data. An important part of the process is called the resampling. Well, what's happening is that in certain cases, and as you can see here on whatever is in the red states, which corresponds to faulty particles, in certain occasions you end up having this is very common actually in particle filtering. You end up having particles with negligible weights, and this when you sequentially recycle them through your algorithm, they cause extreme degeneracy to your filter. So long story short, the resampling essentially cancels out particles with low weights and replicates particles with high weights in an informed manner. So you reassure that there is so you reassure that at the end of each execution there is this modality that pretty much eliminates every like whatever is garbage, essentially particles that don't give you nothing. They do not contribute at all to the description of your PDF. And this resampling approach is a good, like it's exemplifies the association of particle filters with genetic algorithms, because it has this survival of the fittest sort of approach. So at the end, we're having the decision. The decision is that you're getting an estimate of your binary states, which are going to have a value from 0 to 1. And obviously, the closer you are to 1, the higher the chances that a fault may occur. So you define a threshold, let's call it alpha, for which when your binary state, the estimate of your binary state, the mean of your binary state exceeds this value, then you can trigger some sort of a fault alarm. Now, the selection of this value alpha is debatable, and it's and it has to do with many terms. It has to do with the noise level. It has to do with the degree of separation between the faults and the nominal modes, because in the case that they overlap, this is making, when the modes and the health dynamics overlap, then this is going to make your life difficult in distinguish them, but this is a general challenge. Now this is how what's the macroscopic view of our algorithm. Essentially, it is a bootstrap particle filter, as it's called, the most fundamental form of the particle filter. That particle filter that it has exactly the same structure with a particle filter, but it provides identification, fault detection and identification. So I'm not going to spend a lot of time to the results, just a case study. We're having the quadcopter, 12 states, and the fault under configuration is loss in the efficiency of the thrust. Okay, so the force under considerations is we're having 4 thrust vectors, and we can model the loss in the efficiency. In other words, we do not produce as much thrust as you want. So this bolded T is supposed to come, the thrust that you produce is supposed to come from some feedback control law, but at the end of the day, because of our fault, you're already having this T bar, which is going to be it's going to be a scaled down version of your T. So in your continuous valued state, in your FSF filter, you're going to put the 12 state motion variables of the quadcopter. And you're going to also introduce 4 binary variables, each representing a loss in the thrust of one of the rotors. Again, this is we need to discretize. We need to discretize they need to discretize the state equations. Okay, this is how it's going to look like, the block diagram, how this can be applied. We end up having the controller. Then there is another modality, the diagnoser, that takes the aircraft dynamics and also the thrust vector, which is the control signal. Okay, and the fault is injected, and we are making a decision at the end of the day. There is the decision is the dual, so we're having a dual estimate of the state and also these binary states, which help in making a decision whether or not a fault is present. So the idea is, so we're having a quadcopter. It's supposed to hover at an altitude of 100 meters. The simulations run for 10 seconds, and there is, at some point, there is a loss of approximately 20% in 2 of the rotors. You can see that the magenta, or whatever color is that one, is supposed to be a step function that signifies the presence of the fault. The dashed lines are supposed to be the probabilities of failure, and the red line is the decision line. This is what determines whether or not the fault is present. As you can see, when the faults occur to the system, and Vincent tried to do this challenging, he seeded both of the faults at the same time in order to confuse the filter. After the elapse of a number of time samples, the filter confidently identified the fault. A little bit of how the thrusts look like. Those little teeth, those little discrepancies are supposed to be the loss of the efficiency. We also are having how the position looks like. Those are the different, those are the estimated and the actual states. I mean, obviously, there's going to be a difference. Remember that the important thing is the identification part, it's not the estimation part. So, what I presented you today, and I know that my time is up, so I don't want to abuse your schedule. So, so there's a hybrid system formulation. I'm having continuous valued dynamics, and I'm introducing binary states that signify faults. And the idea is to streamline the identification when we are dealing with concurrently occurring fault modes. This approach eliminates the needs for a bank of estimators, making our estimation problem for fault diagnosis much more efficient in terms of computation. And finally, one of the things that we find appealing is that it is very well suited for real-world integration. So it doesn't something that requires nonlinear inversion or some sort of analytical laborious process. Essentially, the only thing that you have to do is sample and in your embedded system and just update your state. Now, I just want to, and I'm gonna make this last remark. Obviously, sampling was always important, but I believe in the last definitely 15 years, sampling and the use of samples to approximate, to provide solutions to unattractable problems is becoming extremely popular. Whether it's motion planning or what is referred to as the path integral control, sampling is proven to be a reliable ally in getting meaningful solutions to problems that we are not able to provide exact analytical maps. Okay. Now, I also would like to make the following connection with reachability. Reachability is this is what Melchior has provided an excellent presentation. It has to do with the ability of a system to reach certain states in a certain time interval, and Melchior, you can correct me if I'm wrong. I just want to comment on the convenience of the particle filters to make prediction that essentially you recycle your trajectory through the model dynamics, and you can conveniently quantify the uncertainty, like approximate the uncertainty of these PDFs through this discrete PDF approximation that the particles and their weights provide. Now, one more, the The superstar here is Vincent Wow. He's my PhD student. This work has been in the past, certain elements of this work, some facets of this work has been sponsored by NSF, and now they are now we are being sponsored by ACRL-UIUC. So thank you very much for your patience, and I'm sorry for taking longer than I should.
Okay. So let's see if there are any questions for you.
Thank you, Ioannis. This is Ali. Could you go to the slide that you were talking about the limitations and just a little bit make more comments on that part, or you didn't grab that aspect?
The moment of, do you by any chance remember that slide? I can provide you a list of limitations right now.
Okay, yes, that might be easier, yes.
Okay, I mean, the number one thing that we've been receiving a lot of heat, and especially these days, is the use of first principle models of state transition PDFs. Everything is geared towards model-free versions and approximations based on data. The number two issue that, but this always existed, it was the computational intensity of the particle filters. If you want to have a good estimate, you need to have a large number of particles, which has been through the years heavily criticized, but it's difficult, it is difficult in certain cases to obtain real-time, reliable real-time solutions. I would argue in this criticism that well, that's the price that we pay in order to have brute computation substitute difficult analytical problems. And finally, like one other last shortcoming, perhaps, is the large variances that are the particle filters subjected. That's not a small thing, obviously, especially when the number of particles decreases. So this is what I would say would be a summary of shortcomings, to my mind, at least.
Thank you.
More questions? So there is a chat question, it seems. Okay, there is a question from Lucky Martin in chat. Could you read it? And
yeah, so it's coming from James, and James argues that in many real-world examples, a fault essentially can be healed, and it provides a specific example. So James, actually, this is not a problem at all, and in fact, we are having variations. I just did not show it today, that we take account of that issue. So what do I mean? This is the case that you judiciously create all the time a minority of particles in the other side. Okay, so your filter is designed to continuously explore transitions, healthy to faulty and faulty to healthy, without biasing to the extent possible the final result. So it's definitely doable. I just didn't use it in this presentation because this is what we had the most recent. Thank you, James.
more questions, if any? if now we can close maybe the chat, the Teams, because we are well over time. And Ioannis, kindly share your slides with us that you used, right? Because we'll use the recording to upload. Thank you, everyone. Good weekend. And next time we'll have James presenting from Lockheed Martin. We have a new team from Lockheed Martin now, and James will present next time, upon which we'll go to invited speakers, because our team is already complete. We'll start having invited speakers, and I have already invited and confirmed Marco Pavone for the April seminar. And if you have good names that you would like to recommend from either industry or academia who had great impact on industry, please send the names to me. I'm happy to invite. Thank you, everyone. See you next time.